All right, we're starting chapter 17, which is acid-base equilibria and solubility equilibria. This will be the last of the equilibrium chapters before we get into thermodynamics. So the purpose of this chapter is to talk about the common ion effect, which is going to describe when an ion is present initially, that how it affects the overall equilibrium. Then we'll talk about buffer solutions. This is really important for those of you in biology. You have to understand how buffers work and how you make those solutions. And then we'll talk about acid-base titrations. You will be doing acid-base titrations in Gen Chem 2 lab, and we're going to talk about all the concepts related to acid-base titrations. The next topic, we're switching gears. We're going to be talking about solubility. So when we add ionic compounds together, some of them stay soluble in water or are miscible and others are not. And we're going to talk about when adding different ionic compounds, when does precipitation occur. I will say for section 17.4, you may want to go back and review chapter 4, the solubility rules. I think it will help you tremendously for this section. And then we'll talk about factors affecting solubility. You know that it's easier to dissolve sugar in hot tea than it is iced tea. So that's what we'll be talking about in section 17.5. We will be skipping section 17.6. So the common ion effect. This is going to be important to understand this concept. It's going to be, you're going to see this over and over again, not just acid-base equilibrium, but also solubility equilibrium. So let's show you how this works, okay? So here we have a 0.1 molar solution of acetic acid. And you know from the previous chapter that acetic acid is a weak acid and that this process is reversible. So we have acetic acid reacts with water, and again, the double-headed arrows are not showing up, and that forms the hydronium ion and the acetate ion. So initially we have 0.1 molar acetic acid, and I don't know, we'll just change it to that. And we know we have 0 of the products, so we know that, again, Q is less than K. We learned how to do that already. We know this reaction is going to go in a forward direction or to the right or to the products. And since it's all, the coefficients here are all 1 to 1 to 1, then we're going to lose X amount of the acetic acid. We're going to gain X amount of the hydronium ion and X amount of the acetate ion. Add those together, we get our equilibrium terms, 0.10 minus X for the acetic acid and X for the hydronium ion, X for the acetate ion. So it says the hydronium ion and the acetate ion, when we calculate X out, it's going to be 1.34 times 10 to the negative 3 molar. They don't show the calculation here because we've learned how to do this in previous chapters. We know if this is the hydronium ion concentration, we can take the negative log of that and get the pH. So the pH is 2.87. That's what we would expect for a weak acid solution. So all this is just review from the previous chapter. But the reason why we're doing this, we're going to throw a variable in here. So what would happen if I added 0.050 moles of sodium acetate? So sodium acetate's a salt. It is a sodium ion and the acetate ion, and so it's an ionic compound. When we put the ionic compound in water, it dissociates into the sodium ion and the acetate ion, and we know they're dissolved in water. It says aqueous here. So now the question is, if we revisit the reaction that we just did, acetic acid reacts with water to form the hydronium ion and the acetate ion. What happens if this is initially present due to the addition of the sodium acetate? Notice the sodium doesn't come into play here. Remember we said sodium is a neutral metal ion. It doesn't undergo salt hydrolysis. So we don't worry about the sodium. It's a spectator ion. We learned about spectator ions in Gen Chem 1. It's an ion that does not participate in the chemical reaction. So what happens if we add sodium acetate? And so initially we have some acetate present, whereas before it was 0. Now we have an initial amount. That's what this little sub-zero means here. So let's see what happens. Well, this addition of that ion is called the common ion effect, all right? The common ion. So how do we know there's an effect due to that? Because if we write the K for this, the K is actually an acidity constant, right? We had the hydronium ion as a product. We had the acetate ion as a product. And then in the denominator, we had the reactant, acetic acid. So this ion is present initially, and how does that affect the equilibrium concentrations for this reaction? So that's what we're going to focus on. So here we go. It says determine the pH at 25 degrees Celsius of a solution prepared by adding 0.050 moles of sodium acetate to a liter of 0.10 molar acetic acid. Assume the addition of sodium acetate does not change the volume. So the volume is going to remain constant. Even though we've added some sodium acetate, and that does take up space, we're going to assume the volume does not change, and that makes this problem a little bit easier. So you're looking at this problem and going, isn't that what we just did? It looks pretty much like the same problem, but the addition of, we have an addition of sodium acetate. So we do an ice table again. So here's the difference. In this ice table, you have this initially, the acetic acid, but now because you've added 0.050 moles of sodium acetate, and it's 1-to-1 sodium acetate to sodium, then that's how much acetate ion we have initially, where that was a 0. All right, so then again, because this is a 0 here for the hydronium ion, Q is going to be less than K, and you know the reaction is going to shift in this direction. It's going to go in this direction. So that's how we know this is minus X here, plus X here, and plus X here. So we add these up, and we get our equilibrium values here. So we're going to plug those equilibrium values into the expression. So here's what it looks like. Here's the Ka for acetic acid. Hopefully by now you've got that one memorized. We've done it so much. Here is the hydronium ion concentration. Here is the acetate ion concentration. We already had some initially, and we're going to add some more as the acetic acid ionizes. And then here is the loss of concentration of the acetic acid as it ionizes. So we're going to assume this X is negligible. And because look at the difference here, it's about 1 times 10 to the 4th difference. And we're going to assume this X is negligible. So that's going to oversimplify the problem so we don't have to deal with a quadratic. And so now this is what we have. We have the Ka for the acid equals X times the concentration of the acetate ion over the concentration of the acetic acid. And we solve for X. So when we solve for X, we get 3.6 times 10 to the negative 5th molar. So what does X equal? So what does X represent? Well, again, don't forget to go back to the ice table, and we see that X represents the hydronium ion concentration, okay? And so knowing that that equals the hydronium ion concentration, then we are ready to, we're ready to calculate the pH. So negative log of 3.6 times 10 to the negative fifth equals 4.44. Oh, 4.44. What was it before when it was just pure acetic acid? Well, let's go back and look. When it was pure acetic acid, we got a pH of 2.87. 2.87. So what that tells us is the pH is it's more acidic, more hydronium ion has been produced to make a pH of 2.87. And now with the addition of sodium acetate, the reaction's not going to go as far to the right as the original reaction. It's not going to go as far to the right because of the presence of this common ion, the acetate ion. And that's why the pH is 4.44. So that's the common ion effect. If one of the ions on the product side is present, the reaction will not go as far to the right to reach completion. Notice the acidity constant. Let's go back. The acidity constant doesn't change. The Ka does not change in this reaction. And if we compared it to the other one, what is making this all happen is the initial concentration of the acetate ion. And we could have had an initial concentration of the hydronium ion. So either one of those would be a common ion effect. In this case, we added sodium acetate, so that's where the common ion effect lies in this reaction. And you go, why do I need to know this? Well, it is the common ion effect along with a weak acid or weak base that is going to give us buffers. And buffers are substances that when we add an acid or a base, the pH does not change appreciably. All right, so it says a solution that contains a weak acid and its conjugate base, so weak acid like HF, and its conjugate base, F negative, the fluoride ion. And again, you can't go out and buy a bottle of fluoride ion, so it's going to be in the form of a salt like NaF, sodium fluoride. And then we know the sodium doesn't affect pH, and then we know that these are ionic, these are ions, and so that's how we generate that's how we have the fluoride ion. We have to add a salt. We call this a salt added to a weak acid. Or you can have a weak base and its conjugate acid. All right, so that's another buffer system as well. These are called buffer solutions. And a buffer's ability to convert strong acid to a weak acid minimizes the effect of the addition on pH. Okay, so what does that mean? That means if I add acid, a strong acid, the hydronium ion, to a buffer system, the hydronium ion will react with the conjugate base of a weak acid and form the molecular acid plus water. So notice on the product side, we do not have either hydronium ion or hydrogen ion or hydroxide ion. So as long as these aren't generated, the pH shouldn't change. As opposed to if I have water, if I have a hydrogen ion and I add that to water, then I'm going to get as a product H3O positive, and that's going to change the pH of the solution drastically. Here, when we add the hydronium ion, the conjugate base of the weak acid reacts with the hydrogen ion and forms the weak acid, the molecular weak acid in water, and we don't see the production of hydronium, hydrogen, or hydroxide ion. And that's the way a buffer works. It can absorb either hydronium ion or hydroxide ion, so we don't see that on the product side, and the pH does not change appreciably. So a buffer has to be able to absorb more than just hydronium ion. It has to also be able to absorb hydroxide ion. So if I add something that's basic to a buffer, the hydroxide ion will accept a hydrogen ion from the weak acid. That will form water, and then we have the acetate ion left over. So again, notice on the product side, you do not see the production of hydronium ion or hydrogen ion or hydroxide ion. Since none of these are produced, we wouldn't expect a pH change. Whereas if you took the hydroxide ion and you added it to water, you would get hydroxide ion in water. I mean, technically what happens, I guess you could say this comes over here and that leaves OH left over, but you still have the hydroxide ion produced on the product side. So if the hydroxide ion is produced, we would expect the pH to go up. Just as on the last one, if hydrogen ion is produced, we'd expect the pH to go down. But here, none is produced. It's absorbed. The hydroxide ion is absorbed, and so the pH should not change appreciably. So again, what is a buffer? A buffer must be a weak acid and its conjugate base, or a weak base and its conjugate acid. Both of those components have to be present. And the reason why both components have to be present is that a buffer has to be able to absorb both acid and base. If it absorbs only acid, it's not a buffer. If it absorbs only base, it's not a buffer. It has to be able to absorb both acid and base. And the way that works is the weak acid, in this case, can absorb hydroxide ion. And if we go back to the previous slide, we can see that, oops, I went too far. We can see that the conjugate base of the weak acid can absorb hydronium ion to make the molecular acid. All right, so here we have our setup here. So it says a buffer's ability to convert a strong base to a weak base minimizes the effect of the addition on the pH. So in order to have a buffer, again, we can see this is going to be a buffer because we have the weak acid present initially, and we have its conjugate base. So this looks just like the common ion effect, right? So that's why we did that first. So here we have this system. We can calculate the pH of this reaction. And again, if I missed those, just know that there has to be a double arrow there. So here's the expression for this reaction. We're going to assume this x is negligible and this x is negligible. And so x is going to equal, we know that we've done this one so much, Ka for this is 1.8 times 10 to the negative fifth. And so we can solve for x, and we're going to get x is equal to 1.8 times 10 to the negative fifth. And we can plug that into take the negative log of that, and we can get the pH. So the pH is 4.74. All right? So this is just a solution. You got a beaker here. Mostly water, but inside the water we have our weak acid, molecular acid, and we have the conjugate base of the weak acid. And the pH of this solution is 4.74. All right, so now what happens when we add 0.1 moles of hydrochloric acid to that beaker? And again, we're going to assume that the addition of the HCl causes, or the hydrochloric acid causes no change in the volume. It makes the calculation much easier. So what's going to happen is we had 1 mole of acetate ion, the conjugate base of acetic acid. We're adding 1 mole of hydronium ion from the hydrochloric acid, 0.1 mole. And then that's going to produce then 1 mole of acetic acid, right? So we had 1 mole to begin with. Okay, so so we had 1 mole of the acetate ion and we had 1 mole of the acetic acid. The 0.1 mole of acid is going to react with the acetate ion, and we've seen that already. that produces, so we lose 0.1 moles of the acetate ion, and that's why we have 0.9 left over. We have 0 of the hydronium ion from the acid because it reacted with the acetate ion. And now we have 1.1 moles of the acid. So we had 1 mole, and then this 0.1 was converted over to molecular acid, and that makes it 1.1 mole. All right? So that's the way a buffer works, is you've got the conjugate base of the weak acid, you've got the weak acid, you added acid, the acid reacts with the conjugate base, makes more molecular acid, and that's what this is, the molecular acid. And so the hydronium ion is absorbed from the hydrochloric acid. So this is what our table looks like now. We have the acetic acid is now 1.1, and then the acetate ion is 0.9, and the hydronium ion has been consumed. So again, Q is going to be, again, you got to do Q. Q is less than K. The reaction is going to shift in this way. That's why it's minus X here, plus X here, and plus X here. Here's our equilibrium values. Plug that into our expression. Here's the Ka for acetic acid. Here are our products, the hydronium ion and the acetate ion divided by the change in the acetic acid. We're going to assume this X is negligible and this X is negligible compared to those concentrations. And we're going to solve for X, and X equals 2.2 times 10 to the negative fifth. Plug that into or look at our ice table. We know that that's the hydronium ion concentration. Take the negative log of that, and the pH is 4.66. So, without the addition of the hydrochloric acid to our acetic acid buffer, the pH was 4.74. With the addition of hydrochloric acid that reacted with this conjugate base, the pH comes out to be 4.66. So that's not much of a change, 0.08 pH units. So that's what a buffer does. It can absorb both acid or base, and the pH will not change appreciably. Now, compare that to, if I take 0.1 mole, if I have water that's at pH 7, and then I add 0.1 molar hydrochloric acid, and that makes the concentration 0.1 molar in the hydronium ion, the pH drops to 1. So we went from a pH of 7 to a pH of 1 when I add 0.1 moles of hydrochloric acid to make a liter of solution, which is 0.1 molar, right? So here's the kind of thing that we get into. If you don't buffer your aquarium and you have a small amount of acid added, that acid is going to cause the pH to drop from 7 to 1, and your fish are all going to die. That's too big of a pH change. One of the things I didn't mention is, remember that every time you change a pH unit, you're changing a power of 10. So when somebody says the pH of tomato juice is a pH of 4 and water's a pH of 7, how many times more acidic is tomato juice than water? Well, that's a 10 to the third difference. That's 1,000 times. So each pH change is a factor of 10. Here we're changing 0.08 pH units. Here we change 10 to the 6 pH units from pH 1 to pH 7. That's where we're going with this. Buffers reduce the changes in pH upon the addition of acid or base. All right, so that's what they just said, the same thing that I said, pH 7 to pH of 1. All right, so in determining the pH of a buffer, we can always assume that the amount that ionizes, the X, is negligible compared to the original concentrations. We also can ignore the hydrolysis of the acetate ion because of the presence of acetic acid. So you go, what does that do for me? All right, let's look at it. So any acid, let's look at any acid. It's monoprotic acid becomes hydrogen ion plus the conjugate base. And we're looking at a weak acid, right? So it looks like that. This is the expression. And the only difference between this expression and this one is I didn't add the water and make this hydronium, but this and this are this equivalent, right? So if I solve for the hydrogen ion concentration or hydronium, that HA is going to come over here, the A negative is going to go down here, I get this expression. And then if I take the negative log of everything that you see here, I get negative log of the hydronium ion concentration equals negative log of the Ka, and the negative log of the concentration of HA, the molecular acid, over its conjugate base. All right, I'm going to flip this. I'm going to flip the HA down to the denominator and the A negative up to the numerator. That changes the sign here. Okay, so now it's plus. You go, why did we do that? Well, people don't like negative logs for the most part, so that's why we did that. And then you know that negative log of the hydronium ion concentration is pH, and negative log of the Ka is called pKa. So now what we have is pH equals pKa plus the log of the conjugate base over the molecular acid. So let's clean that all up. And we get this equation, and you need to memorize this equation. This is called the Henderson-Hasselbalch equation. You must know this equation. And you're going to do enough problems, you'll have that memorized, but this is the important part of section 2 in chapter 17. The Henderson-Hasselbalch equation. pH equals pKa. Remember, P, nothing fancy about P. P just stands for negative log. We saw it when we talked about pH. All right, so negative pH, negative log of this goes here, yeah, and negative log of Ka is called pKa. And then the key here, this is the most missed part, is we change the sign. This is plus now, and it's the log of the conjugate base over the molecular acid. Henderson-Hasselbalch equation. So let's put it to work. So let's look at a problem. It says starting with a 1 liter buffer that is 0.1 molar in acetic acid, 0.1 molar in sodium acetate. Calculate the pH after the addition of 0.1 moles of sodium hydroxide. Assume the addition does not change the volume of the solution. All right, so what we have here is we have 1 molar of this, 1 molar of this, and we're going to add 0.1 mole of this. Okay? So what's going to happen? Well, this hydroxide is going to strip the hydrogen ion off the weak acid. That's going to make this drop down to 0.900 molar. Or 0.9. Yeah, 0.9. Well, that's too many. 0.90. Oops, 0.90. All right, this becomes 0, and this becomes 1.10 molar. Because once this happens, then we're forming more of this, right? And the hydroxide and the hydrogen form water. Okay, so it's kind of like an ice table, same thing. So what we had the initial concentrations, and then we have the, so we got the initial concentrations. Wish these were lined up a little better. All right, this goes here. This is after the change, after the addition and the reaction, all right? And then here's where it's nice. You don't have to do, you can solve this like an ice table problem, and you can do an expression if you want to. But here's how you do it quickly on a quiz or an exam. The Henderson-Hasselbalch equation, pH equals negative log of 1.8 times 10 to the negative fifth, which is 4.74. We saw that calculation in a previous slide. Plus the log of the conjugate base. This is the crucial part, getting this correct. The conjugate base here and the molecular acid here. So pH equals 4.74 plus the log of 1.10 over 0.90 molar. These units cancel out. When you take the log of this, so log parenthesis 1.10 divided by 0.90 close parenthesis, and add 4.74 to it, you get a pH of 4.83. So again, let's talk about what's going on here. We said that in a pure acetic acid buffer, the pH is 4.74. We saw a drop of 0.08 units, so we went to 4.66 when we added 0.1 moles of hydrochloric acid. If we didn't have the buffer, it would have dropped down to a pH of 1. In this example, by adding 0.1 hydroxide ion from the strong base, sodium hydroxide, the pH jumps up to 4.83 for a difference of 0.09 pH units. But if we had 0.1 molar sodium hydroxide, which is a strong base, that would be 0.1 molar hydroxide ion, and the pOH for this would be equal to 1, and the pH would be equal to 13. So without the buffer, the pH would have jumped up to 13 in this situation. Because we had the weak acid there to absorb the hydroxide ion, the pH only jumped up from 4.74 to 4.83. So I hope you see what a buffer does. We can add acid, we can add base, the pH doesn't change appreciably. Without the buffer, the pH changes drastically. For the acid, it would have been a pH of 1. For the hydroxide ion, it would have been a pH of 13. So buffers allow us to have additions of acid or base without changing the pH drastically. So a solution is only buffer if it has the capacity to resist the pH change. So the question always is, well, can I add as much acid as I want or as much base as I want, and I'll always get just a small change in the pH? Well, you can exceed the buffering capacity. So if the concentrations of the weak acid and its conjugate base differ by more than a factor of 10, the solution does not have this capacity. So you need to know this. You need to memorize it. You need to be able to apply it. If the concentrations between the weak acid and its conjugate base differ by more than a factor of 10, the solution does not have this capacity. Make sure you understand that. All right, so let's see how that works. Therefore, we consider a solution of buffer. So here's the Henderson-Hasselbalch equation. And they're saying that the ratio of conjugate base to the weak acid can be no more than 10. The ratio can be no more than 10 and no less than a tenth. If it is, we lose the buffering capacity. So it says, if you take the log of this, it's 1. The log of this is negative 1. And so pH of the buffer cannot be more than 1 pH unit different from the pKa. So if the pKa is 4.74, we cannot exceed 5.74, and we cannot drop below 3.74. If we do, we're outside the buffering capacity, and you need to choose a different weak acid and its conjugate base. So if you want a pH of around 4.74, the acetic acid buffer is a great buffer. But if you want something around a pH of, say, 8, this isn't going to work. So how do we quickly know what's going to work and what's not going to work? Well, the pH equals the pKa plus or minus 1. That's the range of the buffer. That's the range. You find the pKa plus or minus 1, that's the range of the buffer. So here's how it works. You've got a list of potential weak acids and their conjugate bases, and you have the Kas in the table, which we used over and over again in the last chapter. If you take the pKa's, then you're saying HF would be a good buffer if you're going to go no more than 4.15 and no less than 2.15, plus or minus 1 pH unit or pKa unit. So all these buffers, you can then see what the range is. Then after you get the range, here's something that's tricky about this one right here. If you're working in a biological system, you're not going to use that as a buffer because cyanide locks up the hemoglobin, right? It's toxic. It's poisonous. So even though this would be a great buffer between the range of 8.31 and 10.31, you also have to think about what is the substance. This would not be a good buffer for a biological system. Substitute the pH for the pKa, put it in the equation, figure out which buffer is best. All right, so there it is, Henderson-Hasselbalch. Let's see if you can apply this, what we just talked about. So it says select an appropriate weak acid from the table and describe how you would prepare a buffer with a pH of 9.50. All right, so if you're looking at this table, which buffers would be best for a pH of 9.50? Well, right off the bat, you know it's not this one, this one, this one, or this one, or this one. So now we're down to these two. Okay? These are appropriate buffers for 9.50. Okay? So they throw out the cyanide for obvious reasons, especially if you're trying to keep some type of organism alive. And then here's what they have. This is the pH. Here's the Henderson-Hasselbalch equation. This is another way you're going to use it. Here's the pH you desire. Here's the pKa. And then you do the log of the conjugate base over the conjugate, over the weak acid. So we're going to solve for this ratio here. That's what we're going to solve for. And so we would say 9.50 minus 9.89 equals the log of the conjugate base over the acid. And so this number here is equal to negative 0.39. To get rid of the log, we do the inverse, and we get this over 10 raised to the negative 0.39, and we get a ratio of 0.41. So what this says, the easiest way to interpret this is it would be 0.41 moles of the conjugate base, which we have to purchase as a salt, over 1 mole of the phenol here. Phenol. What was that? Was that a phenol? Let's go back. They don't really name it, but that's what we have there. Okay. So we know the ratio has to be 0.41. So the easiest way to solve this problem, just say this has to be 0.41 moles, and this is 1 mole. And that gives you that ratio there. It could be any number here as long as that ratio comes out to be 0.41. Okay, just keep that in mind. But the simplest way is just say 0.41 of the conjugate base and 1 mole of the weak acid. So I want you to be able to do this problem because you're going to have problems like this on the quiz and the exam because it's easy. It's not you don't have to set up an ice table. You know this is the desired pH. You look at the pKa's, choose the one that's closest to that, and then the log of the conjugate base over the acid. Find that ratio and then solve for it. All right, that's where we're going to stop at today. So what we've done today is really talk about all you need to know about buffers, how they're made, how they're related to the common ion effect, how you're actually going back and thinking about in the last chapter weak acid and the salts of weak acids and the salts of weak bases. So a buffer is a weak acid and its conjugate base, we can't just go out and buy a conjugate base, so it's the salt of the weak acid. And then it could be a weak base and its conjugate acid, but you can't go out and buy just conjugate acid. You have to buy the salt of the weak acid. So that's what we see, that when we have both the weak acid and its conjugate base, or the weak base and its conjugate acid, when we add additional hydrogen or hydronium ions or hydroxide ions, the pH does not change appreciably, and that is due to the buffering capacity. So capacity is the ability for a buffer to absorb hydronium, or I'll just say hydrogen ion and hydroxide ion. Once you exceed one of those, either the conjugate base or the acid, the buffer fails. It's no longer a buffer anymore. So once you exceed buffering capacity, the buffer no longer works. So that's kind of a summary of what we did in section 7.1 and 7.2. And our next video will be on acid-base titrations.